So, welcome to the 7th technical session of International Conference on Futuristic Materials. In this session, we will have a plenary talk by Dr. BP Singh from France, followed by an invited talk by Professor MS Akhtar from Republic of Korea, and we will also have some oral presentation by our young colleague. So, in order to conduct this session, I would like to invite Professor S.N. Tiwari, our Dean of Faculty of Science, to chair this session and conduct this technical session further. Professor S.N. Tiwari, sir.
Okay. Thank you, Dr. Ambrish. Am I audible to you?
Yes, sir, you are audible. Can you please start your video, sir?
That is not visible. Dharmen Pratap Singh is visible, but my video, why not it is? No, video is not.
Okay, sir. You please continue, sir. There is no issue.
Okay.
Let me take a few more minutes to welcome our co-chair of this session, Professor Umesh Yadav, sir, who has also joined us. Professor Umesh Yadav, sir, will be co-chairman of this technical session. I welcome Professor Umesh Yadav, sir. And request Professor S.N. Tiwari, sir, to conduct this session.
Okay, thank you, Dr. Ambrish. This is the second technical session of this day. And this is the 7th one of this program. We are having this in this session. First of all, I would like to offer you a very good afternoon before the start of the session. We have the first plenary lecture by Dr. Dharmen Pratap Singh from France. And he will be talking about discotic liquid crystalline materials, a tool for modern photonic and electro-optical applications. And before I invite Dr. Dharmen Pratap Singh, I would like to introduce before the audience a little bit about him, which is known to me. Dr. Dharmen Pratap Singh completed his BSc and MSc degree from the University of Lucknow, and he did his PhD in the area of liquid crystals. He did his experimental work. He worked under a DST-funded project from 2009 to 2012 at Lucknow, and after that, after completing his PhD, he was awarded Young Researcher Award in 2012 by Indian Liquid Crystal Society, and also SPI Best Research Award in ICAMP 2013 at Cambridge University in UK. Currently, Dr. Dharmen Pratap Singh is my 3D conferences at Unite the Dynamic Structure, the Molecularis Masonry Research at France. Before joining this laboratory, he was UGC FIP faculty at DAB PG College, Lucknow. He also worked as Raman Chapak Fellow at France in the same lab. And he is a very talented person, very devoted and very hard worker. To his credit, he has also been awarded 3rd Best Research during IMID conference at South Korea. He has also been awarded Liquid Crystal Beauty Artist of July 2015 by International Liquid Crystal Society. And also he has been conferred Indian Science Congress Young Scientist Award in 2017 at Tirupati. With these words, I must say that he is a man devoted to the probably all aspects of liquid crystalline materials, whether thermotropics or lyotropics, and that application of those liquid crystalline molecules in the development of technology. With these few words, I invite Dr. Dharmendra Pratap Singh to please deliver his plenary talk. Dr. Dharmendra.
Thank you, Professor Tiwari, sir, and thank you for your kind introduction. Before I start my talk, I would like to thank you as a convener and my colleague, Dr. Amrish Srivastava, for inviting me for this to talk over my research work, which I am currently doing in my French laboratory. I would like to express my gratitude to you, Professor Tiwari, sir, when I got Young Scientist Award at the Indian Science Congress. You were the president of physical sciences, and I must admit your support to shape my career as well. So I would like to share my screen. Is it visible to you all, my screen, and I am audible well to you?
Yes, yes,
Yes.
Okay. Thank you. So I will. Myself, as introduction has already been given by Professor Tiwari. Basically, after completing my PhD, I joined a French laboratory called UDSMM at the University of the Littoral Opal Coast in France. And after serving 2 years of postdoc, I joined as a permanent faculty in 2018. And at the present, I am associate professor at University of the Littoral Opal Coast. So today I will be talking about the discotic liquid crystalline material that are the tool for the modern photonic and electro-optical devices. So basically I have covered my talk in several outlines, starting from the introduction, experimentals, what results I have gained, conclusion, and future scope. So I want to introduce where I am. So basically I am in Calais. This city is known as Calais. You can see it's a coastal city with very fantastic panoramic views. I invite you all, if you get any chance to come to France to visit my city as well as my laboratory. We will be hosting 2 conferences as well in September 2021. So I will give the details as well so that you can connect to it. So this is the location where we are. This is the city of Calais. This is the Dunkirk. These are the 2 cities and other cities, because my university has 5 branches over the France, and all the branches are at the coastal areas. So that's why its name is like University du Littoral Côte. And we are just neighbor to England. Only this English Channel is between, and this Calais is famous because a sea tunnel of 25 kilometers goes beneath the sea from France to England. So these are my laboratories situated at the 2 sites at Calais and Dunkirk. So it's really very beautiful panoramic views at the beach of English Channel. So I would like to thank my students who are working hard day and night for obtaining some interesting results. Asmita Sasi joined our laboratory in 2018 as a PhD student, and this year Vinso joined us as a new PhD student. Recently, one master student from University of Mumbai, Ms. Sukanya, has won the TRPL fellowship with our laboratory. So we will be welcoming her in January this. So this is my research team led by Professor Christian Legon and 2 other professors, and there are some other Medu conference like assistant and associate professor along with 2 research engineers. All of you know about the states of matter. So basically you can find any matter into the different state that can be a solid, liquid, gas, and plasma. And when you heat or freeze, you can obtain a different states of matter in any substance. So basically the idea about liquid crystal came that whether any intermediate phase is possible or not. So yes, it is possible. And liquid crystal, basically these are the mesophases. Mesophase mean intermediate phases between crystalline solid and isotropic liquids. So they exhibit both the qualities of solid, like ordering like crystalline solid and fluidity like liquids. So basically you can characterize this liquid crystal into two types, that is thermotropic and liquid lyotropics. So thermotropic is basically mesophase is obtained as a function of temperature, whereas in lyotropics it is like it contains a hydrophilic polar head along with a hydrophobic nonpolar end. So it consists a rigid core and flexible chain so that it gives the mesophase. So later on, basically I work on the thermotropic liquid crystals. So thermotropics can be subdivided into the calamitic, like a rod-shaped molecule only, and disc-shaped molecules. So, okay, so basically in calamitic rod-like liquid crystals, so when you heat a liquid crystalline compound from a crystalline to isotropic liquid, you can obtain different liquid crystalline phases in between. So basically most common phases are pneumatics, osmatics, and in osmatic A and osmatic C. So basically in the pneumatic liquid crystal, what happens, the molecules obtain a average molecular direction that we call the director. So director is the average orientation of the molecule. So that's why it contains only the orientation or order parameter. So in the osmatics, a layer structure is formed due to the alkyl chains. And this molecular director is parallel to the layer normal in the osmatic A phase. That's why it contains orientational order parameter as well as a weak positional order. But in osmatic C, this director is tilted with an angle theta with respect to layer normal. So this is the tilted phase. And you can obtain the order parameter in different phases. So for the crystalline phase, its order parameter will be 1. For the isotropic liquids, because there is no order at all, so order parameter will be 0. And order parameter for the liquid crystalline material lies between 0.2 to 0.8. You can calculate the order parameter using this formula. And different mesophases can be observed by the polarized optical microscopy under the cross polarizer analyzer condition. So here I will show you how you can obtain the mesophase. So when you heat any pneumatic compound, you can obtain a very fantastic birefringent texture. And with respect to temperature, like you can obtain thread-like texture, especially the defect as well. Okay, and when it goes to isotropic phase, it becomes completely black. So I will not, I think it should take some time to go to the isotropic phase. We can wait here and we can see. So because it will depend on the temperature range of the compound, like for how much interval of time it exhibit the pneumatic phase as well. And now, yes, it's going little in the isotropic phase. So when it goes to isotropic phase, the structure become completely black. So now the question is, do only rod-like molecule constitute a mesophase? So it was a myth till 1977 that only rod-like molecule can constitute a liquid crystalline phase. But in 1977, S. Chandrasekhar and his team at Raman Research Institute, they shown that not only the rod-like molecule, but also disc-like molecule can constitute a mesophase. And later on, it was known as discotic liquid crystal. So basically, discotic liquid crystal also constitute a core, that is a pi conjugated aromatic core, and it is surrounded by alkyl chain as well and extended functional groups. So based on the different, like 70 cores, more than 3,500 discotic liquid crystal has been synthesized so far. So why it is important for the modern organic electronics? Because due to the pi-pi stacking, these molecules can form a self-assembly in a column, and later on they can be arranged in the hexagonal matrix, rectangular matrix, and so on. So the core distance between the two columns is around 20 to 40 angstrom, whereas the core separation along one column around 3.5 angstrom. So basically quasi one-dimensional charge transport takes place along the column via hopping. So electron or holes, they hop from one core to another core. So why these are interesting? Because this molecular mobility is very, very high in the organic compounds, and up to 1 centimeter square per volt per second. And the electrical anisotropy along the column and perpendicular to column is very, very high. It's approximately 10 to the power 10. So these disc-coating materials are very good for the TFT, photovoltaic solar cell, one-dimensional conductors, and LED, and so on. So basically here we are dealing with the electronic property, electronic, electro-optical, and photonic property at our laboratory. So basically we are expert in the charge carrier mobility measurements here in the organic devices. So as you know that you can measure the charge carrier mobility via Hall effect in the inorganics. You can also measure the mobility with the space charge limited current method, that is actually the Gurney model. And nowadays people are also measuring the mobility using a field effect transistor as well. But here we are specialized to measure the charge carrier mobility using time of flight setup. So it is a very simple setup. It consists of a laser, pulse laser. We use NdYAG here, and we can tune this wavelength, radiation wavelength, but we use 355 nanometer. And these are some other specifications. So what happens when we irradiate any material with the laser light? So because these liquid crystals are semiconducting in nature, so what happens, they produce excitons. Excitons is like, you know, it's a bound state of electron and hole, but they are not stable. So what happens, they separated due to the thermal dissociation. And later on, when we apply the positive field in between the electrons, between top and bottom electrodes, what happens, hole propagate from top electrode to bottom electrode. So basically this technique is really very fantastic to measure separately the hole mobility, electron mobility, as well as if your sample contains the ions, you can also estimate the ionic mobility. So if you produce negative charges like negative potential here, then electron will move from here, and you can estimate the electron mobility. So in general, we should obtain this type of transient photocurrent curve, and we obtain basically two types of transient photocurrent curves, that is non-dispersive and dispersive. So by measuring this transit time, we can calculate the mobility of the material. So we have investigated the different systems, and basically we are working on the triphenylene core based system, triphenylene and extended triphenylene based system. So basically we investigated some pristine triphenylene based compound, then phenazine fused triphenylene compound, and then pentaalkynylbenzene dyads based triphenylene system. And the papers has been published already. This is under communication because we are modifying one theory of charge transport. We also investigated some triazole-modified perylene tetraester, as well as we doped our HAT compounds with C dots and CDS nanowires as well to see the effects. So basically here what I am presenting is has been done with the collaboration with my Indian colleagues. So Professor Kumar, who is helping us in thesis subject by synthesizing this material. So he's one of the partner and visiting professor in our university. So the first system is the triphenylene core systems. So this is the chemical structure of triphenylene based discotic liquid crystal. So here you can change the length of the alkyl chain, and you can put n is equal to 3 to 13. So basically 3 to 13, they all do not show the mesophase, but from 4 to 3 to 13 they shows 4 to 13 they shows your mesophase. So here you can see as you increase the alkyl length, alkyl chain length, the isotropic temperature reduces. Okay, so but molecular ordering can also be changed so that charge transport property and mobility values are also changed. So here we have shown you the photocurrent curves for the H84, 5, 6, and 8. So you can see here we can obtain a very good transient photocurrent transient curves. So by estimating the transit time, we calculate the hole or electron mobility using this formula. So here it was little discussion about the charge carrier mobility nature over as a function of temperature. So basically triphenylene-based compound, they show a temperature variant charge mobility. And depending on the alkyl chain length, its mobility reduces, but over the temperature, it is almost constant. So why mobility decreases from H84 compound to 8 compound? This is due to the short range electrostatic interactions. So these short range electrostatic interactions, they basically explain you the molecular packing. So when molecular packing or molecular ordering reduces, the charge carrier mobility also reduces. So basically one important interesting idea it came in our mind that why it is reducing, can we estimate any empirical relation for this triphenylene compound? So we went into the literature and we found that if we increase the core size, so if we increase the core size, charge carrier mobility decreases. So the first paper came with the microcyclic cores in 2001. And later on, after 3 years in JAX, this empirical formula was again proved for the alkyl substituted polycyclic aromatic cores. But in our case, because the core is not changing, only the alkyl chain is changing, so we have justified the validity of this expression in our system. And we found, yes, this formula is also valid in our system in order to prove the role of alkyl chain. But the constant A and B, they are not the same as explained by these previous reports. So in the second system, which has been published in New Journal of Chemistry and Chemistry Select, another one student of Professor Kumar, Mr. Atswat Gaura, he fused this triphenylene compound with phenazine compound, phenazine moiety. So before measuring this charge carrier mobility, we have to see whether this compound is eligible to absorb the light of the laser radiation. So we did some photophysical applications. So because we irradiate the sample by 355 nanometer, so it can absorb here 355 wavelength, 355 nm. So this is the suitable condition for the time of flight measurement. And later on, we also doped this compound with some CDS nanowire. And we found that, yes, there is a change in the morphology. So optical texture has been changed of the this room temperature phenazine fused triphenylene when we add the CDS nanowire. So we wanted to check its a property of the charge carrier mobility as a function of temperature. Before some time, I have told that there is a electron or holes, they propagate along one column via hopping process. So the core separation distance between the core is really important. So our idea was, can we reduce this core separation distance so that hopping distance will be reduced, and we can eventually increase the charge carrier mobility. So here, after the doping of the CDS nanowire, we found that, yes, we are obtaining a little reduced hopping distance. So it was very interesting that we will be finding enhanced mobility. But what happened when we investigated the mobility as a function of temperature, we found that it has been reduced. But one interesting thing we obtained, that here the whole mobility increases as a function of temperature, which is not usual in the case of triphenylene. So we went into the literature again, and we were trying to discover what is happening. And then we found that if this discotic liquid crystal and one column, if it is behaving like single crystal materials, because in single crystal materials, the charge carrier mobility increases using this power law as a function of temperature. So we have fitted our charge carrier mobility versus temperature curve using this power law, and we found, yes, it's following this law. But N is greater than 3 for the PFT, and for the doped system, it is N is equal to 2.4. But in case of single crystalline material, the value of these exponents are not the same. So this means that if the growth of the columns are according to the single crystalline material or alike single crystalline material, our system can also follow this power law. And one more important thing, that in discotic we are always interested to develop the monodomain, because if molecular ordering will be reduced, if multi-domain textures is there, so it was one effort to create a single domain system. So after this, we also fabricated some heterojunctions using this PFT DLC. So we have fabricated the ITO and this system here, and the thickness of the ITO, PFT, CTS, and AU is like this, is the parameter here, and we measure some IV curves here. So IV curves show like a ohmic behavior, and but obviously the resistance of the PFT plus CDS is reduced as compared to pristine PFT systems. So these follow this equation. Equations are mentioned here, and we found that yes, our system is following the Poole-Franklin conduction mechanism, but under a limiting condition that this part is equal to 1. So that's why if J is directly proportional to V, it will follow this equation, and the limiting case of Poole-Franklin conduction mechanism is true for our system. The results are published in New Journal of Chemistry. If you want to more detail, you can go to that paper, or I will be love to answer your question if you have any. So after these compounds, we have another collaborator, Professor Santanu Pal at IISER Mohali. So his group is also working on the extended core DLCs. So what he has done, he has attached a pentaalkynylbenzene dyads along with this triphenylene core. So this system will be like electron-rich system, and he doped this electron-rich system with the electron-deficient system in order to obtain the ambipolar charge transport. So he doped this system into different system, and he found the hexagonal column are matrix, hexagonal column are rectangular as well, and in intermediate symmetric phase as well. So he proved that yes, this compound shows the mesomorphic properties, and we did for charge transport properties from him. So obviously this due to the heavy bulky nature, we obtained a dispersive curve in the charge transport, but we obtained the ambipolar charge transport for these compounds, and in which like electron mobility and hole mobility, they are almost temperature invariant, but electron mobility is higher in this compound, but the difference is not so prominent. So later on, he synthesized again some triazole-modified perylene-based system, because perylene-based system, they are very cheaper as compared to the previous system shown of the discotic. And he varied the alkyl chain length, and he saw the variation of in the meso phase. And we again did charge carrier mobilities for these compounds. So, and we found that yes, if molecular architecture is heavy or bulky, we obtain dispersive type of transient curve. And for this, we also obtain very fantastic mobility for this compound. And the electron mobility is again is almost temperature invariant. We recently published this paper in Journal of Materials Chemistry. So why we are talking about the photonic applications of discotic liquid crystals? Because they are fluorescent in nature. So basically based on these triazole-modified perylene tetraester and triphenylene-pentaalkynylbenzene dyads, we fabricated some OLED application with the help of our Taiwan collaborators. And it is shown that perylene-based compound, they show a green OLED application with the efficiency of 6%. So it's a really a very great achievement. And later on, blue LED is not common with the discotic liquid crystal. It's a very rare. So with the using the triphenylene-pentaalkynylbenzene dyads, we fabricated the blue LED. The structure is shown here, and we obtained the blue LED characteristic using this system. However, the efficiency is low. Current efficiency is only 2%. So still we have plenty of opportunities to work in this regime as well. And later on, we also used to disperse some carbon dots in different HAT matrix. So in this study, we dispersed some carbon dots of size 7 to 8 nanometer in diameter in the HAT4 matrix. So what happens, because these nanomaterials, they have a characteristic to form the self-assembly or self-networking. So we found that these carbon dots, they prepare a self-assembly in the HAT matrix. And very interesting, its conductivity enhances 1000 times. However, due to the changes in molecular ordering, we obtain little lesser charge carrier mobility here. So what is the future? Especially is because as you know that all especially the display industry is saturating using liquid crystal, and it is coming in the OLEDs and so on. But still, like discotheque have a plenty of opportunities in future. So basically we are running 2 PhD projects. So first PhD project of Ms. Asmita Shah is focused on the use of discotheque material in the organic photovoltaic devices. And the current PhD with the Vincent, the new PhD student with me, we have formulated some aspects of energy storage application of the discotheque. So preliminarily, he synthesized 2 materials based on the HBC molecules, and he substituted the lithium complexes on the peripheral chain of the discotheques, and we are getting some interesting preliminary result in order to storage the energy as well. So I must thank my all collaborators from the India and other part of the globe. So basically from the India on the discotheque, we are collaborating with Professor Sandeep Kumar at Raman Research Institute of Bangalore and Professor Santanu Pal from IISER Mohali. In addition, we have several collaborations with Professor Sanjeev Inamdar. We are doing some photophysical applications and time resolved photoluminescence applications with him. Professor Pathik Kumbhakar, Raju Manohar, Achal Kumar CVL Maggar in sense, and some other collaborator from the other part of the globe. So basically we receive funding from the different bodies for some mobility project and thesis project. So I acknowledge my all funding partners as well. And because sometime I think this is my moral responsibility to make Indian students aware, because when we were doing our bachelor and masters, we were not knowing about the career opportunities, how we can do. So here I would like to inform master student that next thesis project call in all universities in France, they will be open in January. So if master students, they are interested for joining France as a PhD student, they can look into the call. We also invite application with the Charpak exchange fellowships for masters and PhD student. Recently, one student won the Charpak exchange with us. We have other excellence program by campus farm itself, that is the IFIL excellence programs for the master and PhD student. And we have also the CEFI-PRA, that is the India and France collaborative research system. So Raman Charpak exchange programs are also available for the PhD student. So normally you can go to my website and details are there. And if any master student, PhD student, or any research faculty, if it is he or she is interested to join any exchange program, on behalf of my laboratory and university, I welcome you all. So it is little information that we are hosting 2 conferences in September 2021. So first conference is on the auto assembly and the anisotropic systems. That will be held in 31st August to 3rd September in 2021. This is the first conference. You can type this, you can go, or you can just go to my webpage and you will find the description here. And the second conference and summer school will be going on in September also. So energy, summer school on the energy will be held on 13-14 September, whereas the conference will go on 15 to 16 September. So it will be on the dielectric materials and application, but scopes are not limited only with the dielectric materials. It is up to the all field of science and technology. So thank you so much for your kind attention. And I would like to say that let's begin playing with the new semiconductor discussions. It still have plenty of opportunities. Thank you so much.
Thank you, Dr. Dharmendra, for giving a very nice and elaborative lecture on the different aspects of discotic liquid crystals. Just I have one query. Are you getting any challenge from the organic light emitting diodes?
Yes, sir. We are actually basically the stability is one problem because we have to stabilize this discotic material, and if they are not room temperature discotic, we are facing some problem when the stability. Second is the durability because at the moment we don't know how much durable it will be as compared to the conventional LEDs in the market. And second thing is still like we have to optimize the several thickness parameters and interfacial losses. So these are some challenges as well. We should acknowledge them, and maybe it will be a challenge for not only me, it will be a challenge for the community as well.
For the liquid crystal community.
About some solutions.
Okay, this was a very good lecture, as we all have heard, because LCDs have a threat by OLEDs. And so very much effort is needed in this direction to cope up with the situation.
That's why most of LC scientists, they are moving in this field from LC, liquid crystal to light emitting diode field as well.
They are moving. There are two questions, I think, in the chat box. Since we are running already out of time, with the constraints of the time, I just say thank you for giving a very good lecture and helping us in organizing this conference.
Thank you so much.
Thank you, Dr. Dharmendra.
Thank you, and thank you to all our organizers, including the Amrish, who invited me for this. Thank you so much. Thank you, everyone.
Now, there is a invited talk in this technical session, and that invited talk will be given by Professor M.S. Akhtar, M. Shahid Akhtar. He completed his PhD in chemical engineering from Jeonbuk National University, Korea. Presently, he is working as an associate professor at the same university. His research interests are photoelectrochemical characterization of thin film semiconductors, composite materials, electrode materials for solar cell applications. So far, now, he has published more than 170 papers, and he has also edited 7 books. He is also the member of International Solar Energy Society. We may see that Professor Shahid has contributed a lot to the field of scientific community, not only by doing his research work, but also by publishing nearly 200 papers and editing 7 books to his credit. He is going to deliver a very good lecture in this session, and the topic of his talk is growth of the perovskites solar cells, perspectives of 2D layered materials. With these words, I invite Dr. Shahid to please give your invited talk. Dr. Shahid.
Okay. Thank you, Professor Tiwari, sir. Thank you very much for your nice introduction. So first of all, I would like to thank Dr. Amrish Srivastava and Professor Tiwari sir to invite me to deliver my work. So I'm sharing my PPT. So can you see my PPT file?
Yes, it is visible.
How about my sound is perfect?
Wow, perfect, perfect.
Okay. 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 So first of all, I would like to thank the organizing committee of the International Conference on the Futuristic Material. And I would like to thank Dr. Amrish and Professor S.N. Tiwari sir for inviting me to deliver a lecture. So today I'm going to speak on the growth of the perovskite solar cells, and I will just little bit explain you about the 2D layer materials and its perspective in the perovskite solar cells. So here is the content of my talk. So I will do the brief introduction of the perovskite solar cells, and then why these kind of solar cell is the emerging thin film technology. And then I will show you some of my laboratory work on the whole transporting materials and 2D materials. And finally, okay, I will do the conclusion. So maybe most of you aware about the thin film solar cells. So based on, I mean, their manufacturing, so we can characterize the solar cell in the 3 generation. So first generation, that is we call the commercialized solar cells, so which is on the vapor waste. So we all know about the silicon solar cell is the commercialized silicon solar cells. But why? Because their efficiency is very high, around over 25%, and their stability is over 12 years. But in the recent year, like the majority of the solar cell researcher and scientists, they are focusing on growing the thin film solar cell technology, especially in the recent year, last I think 8 to 7 years, the people, they are focusing on this kind of low cost, high efficient thin film solar cell. So in the recent year, because of the high performance and good stability, the many people, they are focusing on the perovskite solar cell. What happened? So among the all kind of the thin film solar cells, so if you look like in the recent year, the organic solar cell and perovskite solar cell, these 2 cells is highly emerging thin film solar cell technology. Why? Because they are recently showing the very high performance. As you can see in case of the perovskite solar cells, it shows remarkably high power conversion efficiency over 25.2%, which is very close to the single crystalline silicon solar cell efficiency, which is around 27%. And similarly, in case of the organic solar cell, also one of the emerging thin film solar cells, because in the recent year, last year, one of the Chinese groups, they reported the performance of the organic solar cell is over 18%. So neck to neck, because if I'm working on the organic solar cell, so we can use the same materials, in the perovskite solar cell also. So the first question is arise, when we are going to perform the research on the solar cell, how to compete the commercial silicon solar cell. So the best way is if we reduce the production cost of the silicon solar cell. So by reducing the production cost of the silicon materials, automatically it can reduce the cost of the electricity. So in the recent year, the scientists and researchers, they are trying to reduce the price of the electricity is less than 50 cents per watt. So there are the 2 possibility in the thin film solar cell, essentially the dye-sensitized solar cell and perovskite solar cells. So if the dye-sensitized solar cells, if we replace the traditional iodide coupled redox electrolyte by using the half voltage electrolyte like cobalt complex, using the cobalt plus and cobalt 2 and cobalt 3 couple based electrolytes. So by this way we can improve the performance, and then we will reach the efficiency around over 15%. And then another way, I mean, if we just modified the perovskite solar cells by means of like by changing their component like the STM layer, ETM layer. Maybe I will explain you, and then some like the engineering in the perovskite layer. So here is the if you look this figure, so we can easily understand why, I mean, the many people, okay, they are doing the research on the perovskite solar cells. So this is the main reason. In a very short period, you know, if we look the starting year, okay, of the perovskite solar cell research is year 2009. So in the 2009, the one Japanese scientist, they reported just the performance of the perovskite solar cell is around 3.8%. But within just 11 year, okay, you can see the performance of the perovskite solar cell is near to the single crystalline silicon solar cell. So that is the main reason, okay, why our group, okay, doing the research on perovskite solar cell. So if we just let's conclude, okay, why the perovskite solar cells is superior, okay, in the area of the thin film solar cell. So the first reason is like its high efficiency is over 25.2%. Another one is we can easily manufacture we can using the facile low temperature solution based fabrication method, and also the using the perovskite materials in this solar cell it shows the high absorption coefficient, and also these kind of solar cell is highly stable in the air condition. and the interesting things, I mean, in the perovskite solar cells, which shows the high open circuit voltage, which is which is over 1.1 volt, which is much higher than the silicon solar cells open circuit voltage. So just I will maybe the most of you, okay, aware about this one, but I just briefly, okay, explain about the why the perovskite material, okay, is suitable for the solar cell. So the perovskite materials, okay, which follow the equation ABX. So A and B is the two cation. So among A and B, one is the big cation, another one is the smaller cation, and X is the halide. So usually the A is the organic cation, which is like the commercial one, or we can say the reference one is the methylammonium cation, and then B is the lead, and then X is the Cl. So whenever, I mean, we are fabricating the perovskite solar cell, so we always, okay, compare our device performance with the reference perovskite material, that is the methyl ammonium lead iodide. And then good thing, okay, of this kind of perovskite structure, okay, this kind of perovskite material, it shows the high absorption coefficient, which is like the 10 power 4 to 10 power minus 5 centimeter inverse, and it has the small exciton binding energy, which is 2 milli electron volt, so which is highly helpful, okay, for the separation of exciton. And of course, okay, this showing the very good charge mobility, so that's why the charge injection, okay, is faster than the Dyson size solar cell. So these kind of perovskite materials we can easily, I mean, manufacture at the low temperature. We can using the solution process. And the another interesting things, okay, in the perovskite materials, it has the tunable band gap. So it means that if we change the A, B, and X, so it can change the band gap. Like you can see, okay, in this picture. So if, I mean, we change this MA by the FA, you can see, okay, the HOMO and LUMO value of the perovskite is changed. Similarly, okay, if we change the lead by the SN, it can also change the band gap. So this is also like one of the important characteristics of the perovskites. That's why it is highly flexible. Okay, so we, according to our need, okay, we can change or we can tune their band gap. And this is just like the brief principle, okay, of the perovskite materials, because I am going to explain you about the role of the whole transporting materials and electron transporting materials and perovskite. So the principle of the perovskite solar cell is very similar to the solid state Dyson size solar cells. So when the light is illuminate on the solar cell, so the synthesizer, that is the perovskite, is absorb the light and inject one electron to the conduction band of TiO2, and this electron travel to the outer circuit and then generate the electricity. And then remaining holes, it can be, I mean, the collected by the whole transporting materials and transport to the top layer. So this is like the simple mechanism, okay, which is very similar to the solid state Dyson size solar cell. So in the reference device, okay, we usually use the mesoporous TiO2 layer, metal oxide layer, and then perovskite is the methyl ammonium lead iodide, and then HTM layer is the spiro-MeO TAD. This kind of spiro materials, you can see this is the spiro-MeO TAD. And so far, okay, there are the three kind of the perovskite solar cell exist. One is the, we call the mesoscopic structure or mesoscopic perovskite materials, perovskite solar cells, planar structure of the perovskite solar cells, and inverter. So the difference, okay, between the three is the, in case of the mesoscopic mesoporous structure, okay, we usually use this kind of mesoporous metal oxide layer, so which has the many mesopores on the surface, so which is helpful, okay, for absorbing the perovskite layer. And then in the planar, we are using the compact layer of the TiO2 and then making the layer by layer structure like this. Just invert, okay, the regular planar structure, we have the inverted planar structure. So inverted planar structure usually, okay, has the less hysteresis as compared to the regular planar structure. So there are the, like the, in the typical perovskite solar cells, so there are the some issues, okay, like in the normal, this green line, okay, is like the, if our cells has the no issue, it means the no recombination sites or no any trapping sites in the cell. So the normal, okay, current flow is do like this, but the red color, okay, is indicating the recombination sites. So these kind of, I mean, the issues, okay, we can solve by just do some kind of molecular engineering, surface modification of the whole transporting materials, and also, I mean, the choosing the suitable homo type like material. Maybe I will show you like the 2D layered materials nowadays is very famous, and then some thin film manufacturing engineering we can also adopt to solve the these kind of issues. So the first part, okay, of my talk is like the, I will show you some of my laboratory work. So whole transporting materials. So whole transporting materials is the key materials, okay, or key layer in the perovskite solar cell. So that's why we call the heart of the cell is the STM, whole transporting material. So the main role, okay, of the STM is prevent the direct contact between the perovskite and metal layer, and minimize the charge recombination and avoid the degradation at the metal perovskite interface, and also the extract the positive charges, that is the hole, from the perovskite and transport them to the top electrode, it means the metal layer. So the reference device, that is I mentioned before, so there we are using the STM materials, but this kind of STM material, that is the spiro-OMe TAD, so which has the biggest problem is the stability, and another problem is the cost. So far, okay, like there are many companies, okay, chemical companies, they are producing this kind of spiro-MeO TAD STM materials, but the cost, okay, still is very high, like the $500 per gram. So in order to, I mean, the avoid, I mean, that these kind of issues. So this just inclined, okay, or like the ask us to do the research, okay, or developing the new kind of whole transporting materials. So this is the so far, okay, like these are the candidate, okay, for the whole transporting materials. So we have like the organic whole transporting materials, we have inorganic, and then some carbonious whole transporting materials. So in our laboratory, we are focusing on the small molecule based STM materials, or we can say that like the small organic electronic materials. And the sum of like the last year, okay, one of my student, he's working on this kind of inorganic STM materials. He's using and modifying the nickel oxide and then use as a STM layer in case of the inverted perovskite solar cells. So there are like the some carbonious whole transporting materials. So there are several reports, okay, where they just replace the STM materials and using the carbon in place of the STM, and then they say this is the whole transporter free perovskite solar cell. So far, I mean, there are various, I mean, the STM materials. So the dominance, okay, STM material is the spiro-based material. So like this kind of spiro-based material, it shows the performance is around 20%. But in spite of the spiro materials, okay, there are like the several other materials like this kind of fused fluorine derivative STM materials, which is also used for fabricating the perovskite solar cell. But the performance of this kind of solar cell is very low, maybe because of some stability issues, okay, and then maybe at the higher temperature it's not stable. And also there are like the Triazine based STM materials also we use, but still the same problem is like associated with the stability, and the performance is very low. So in our laboratory, I mean, we synthesize this kind of STM materials, thiazole type materials, and then we found, okay, it shows the very good electrical property, like the optical property shows the whole visible region, and also showing the good quenching property, okay, with the perovskite and TiO2, and also show some like the good alignment, okay, with the homo level with the perovskite homo level. And when we check the performance, so performance is around 10.6%, okay, in case of the STM2, that is have the 2 thiophene with the 1 furan. The main reason, okay, for improving the performance in this case is it shows the high electron transport rate, and also it lower the recombination lifetime of the electron. So that's because of that it improved the JSC and VOC. Also we recently, okay, we published one paper, okay, which is based on the thiazole, so in which we using this kind of triphenyl moieties, and when we check the performance, so the alignment, okay, with the perovskite homo level is perfectly matched. And when we check the performance is showing the performance is around 16.4%. And this is the main reason, okay, why, because we also perform some kind of plasma oxygen plasma treatment, so which significantly, okay, improve the faster rate of the electron, and then that's why the decay time, okay, is decreased, so that increase the fill factor and VOC of the perovskite solar cell. And we also have some inorganic, so I'm just skipping this one. Like in our laboratory, okay, we are focusing on this kind of nickel oxide based STM materials. So far, okay, with the perovskite solar cells, there are several issues, okay, is also associated, like some degradation of the device is associated with the moisture, temperature, some electric field, oxygen, and UV light or instruction. So these kind of things, okay, in the last 2 or 3 years, okay, like many people, they are focusing on just introducing the 2D structure first in the perovskite materials, and then just changing the STM and ETM by the 2D materials. So just I show you 2 or 3 slides. So like this one, okay. So as we know, the typical ABX3 type perovskite show the 3D structure. So if we introduce, okay, this kind of long chain, okay, spacer in between the 3D structure, so that make, okay, the 3D structure, and that change the 3D structure to the 2D structure like this. So good thing, okay, by introducing this kind of spacer in the 3D structure, it's increase the performance as well as, okay, is increase the stability of the device. You can see in this case, the device performance, okay, is almost, okay, stable for the 300 hours. So it means the, like the almost the zero, okay, degradation after 300 hour. Similarly, okay, in the other case, if the cap, okay, like the making the layer by layer, so 2D layer, 3D layer, and then 2D layer. So like this kind of layered structure, a kind of the quasi, okay, perovskite solar cell. So they also found the the stability of the cells, okay, is improved up to the 1000th hour, which is very, I mean, the like the remarkable, okay, in the area of the photovoltaic, in the area of the perovskite solar cells. So in the last 2 years, okay, the many perovskite solar cell people, they shifted, okay, their research on the development of this kind of 2D layer materials like the antimony, MXene, transition metal dichalconides, and phosphorine. So these materials, okay, themselves, they shows the 2D structures, and especially, I mean, the we can design, okay, by using these kind of materials very thin, okay, the single or 2-layered 2D structure. So I will show you some of like the example, like here is the why, I mean, these materials is promising, because if we compare, okay, the existing perovskite solar cells structure with this 2D band gap of the 2D materials, so you can see, okay, like this kind of TMD materials, MXenes, phosphines, like their band structure, okay, is almost similar, okay, to our existing perovskite solar cell component. So here is some example, like the in 2019, okay, the one group, they used MXene as a electron transporting layer. So what they did, so they just mix, okay, this kind of MXene, like the titanium carbide with the tin oxide, and making the very thin layer, okay, you can see it's very thin, less than 50 nanometers. So that is enough, okay, for absorbing the this kind of perovskite materials. And then when they check the performance, they found the efficiency, okay, is over 18%, like this one. And when they check the stability, so stability is also much improved, around like the 8 to 10%, okay, efficiency is decreased after the after the operation of 700 hours. Then another like the antimonine type materials, also like the antimony, okay, just like simple grinding, okay, and making the layered structure. So we can also use as a whole transporting material. So very thin layer, okay, less than like the 50 nanometer layer, we can just insert, okay, and then we can design the inverted structure like this one. And it also shows the very good, I mean, the like the performance is over 20%. And the good thing is that using, I mean, this kind of antimone, it not showing the any kind of hysteresis, okay, while using the forward and reverse scanning. And then also like the in the most, I mean, the interesting, okay, materials in the 2D materials, that is the TMD, transition metal dichalconides, especially the MOS2, is like the highly used, okay, materials in the last 2 years. The many people, okay, they are focusing on developing the this kind of TMD materials for fabricating the solar cells. So some people using as a STM material, some people using as a active buffer layer, because it can also improve the interface between the perovskite and STM layer. And you can see, okay, it's also improved the efficiency, the stability of the solar cell is like this. So around like less than 10%, okay, only decrease after the operation of thousands hour. So now the conclusion, okay, of my talk is so by adopting this kind of new technology like the oxygen plasma and APZ plasma treatment, so which can improve the surface of the flexible substrate as well as the glass substrate. So like the hydrophilicity we can improve, and also I mean we can design the different types of the STM small organic materials which can use as a STM material and which can suppress the charge recombination. And also in the recent year, we can use this kind of novel 2D layered material, which shows the great promise, okay, towards the realization of the robust and highly efficient perovskite solar cells with the impressive, okay, long-term operational stability. So thank you very much.
Okay, okay, Dr. Sahir,
Yes.
for giving a very nice lecture. And this is of applied nature, in fact, because we are all facing a very uh, hard problem of this clean energy.
Yes.
And in this direction, you are doing a very good work, and we are all
Thank
benefited
you,
by
sir.
your lecture. And
Yeah,
I
thank you, sir.
think that everyone who is connected must have learned a lot from your lecture. Due to paucity of time, we I'm not going to invite questions. So just I will say thank you for giving yes, such a nice lecture and participating and gracing our this conference. And I hope that again, whenever we will need, you will be available to us.
Definitely, sir. Definitely,
So thank you,
I
Dr.
love to
Akhtar.
do. Yeah. Thank you, sir. Thank you very much, sir. See you
So
soon.
we have two talks in this session. One by Dr. Dharmendra Pratap Singh from France on discotic liquid crystals. And in fact, liquid crystals are facing challenges from organic light emitting diodes. And the second one by Dr. Sahir Akhtar from Korea, South Korea. So he also gave a very timely lecture based on the generation of clean energy, in fact, with the help of 2D layered materials. I thank both the speakers, and now I turn the mic to my colleague, Professor Umesh Yadav, to close the session and start a new session as the chairman. Professor Umesh Yadav and Dr. Ambrish, thank you for inviting me to chair this session.
Thank you, sir. Let me add that we want to welcome Dharmendra Pratap Singh as a co-chair of this session.
Okay.
I request Umesh Yadav sir to start this session.
Thank you, Dr. Ambrish, and thank you, Professor S.M. Tiwari sir. So this is the last session of this conference. This is I can say that this is the part of technical session 7, in which there are 6 oral presentations of 10 minutes each. So I would like to invite first oral presentation by Dr. Vinita, Chemistry Department, DDU Gorakhpur University. Dr. Vinita.
Good afternoon, sir. Thank you, sir, for giving me opportunity to present my work here. May I audible, sir?
Yes, yes, please.
Okay. So here I was sharing my screen and present my work. My research work is mainly based on the nanomaterials, and the nanomaterials act as artificial enzymes. So I am Dr. Vinita from Chemistry Department, and I have done my work with the collaboration of my supervisor, Professor Rajiv Prakash from Indian Institute of Technology, BHU. So as we know that the nanomaterials are very small in size, from 1 to 100 nanometers in size, and they possesses different extremely extraordinary properties like high thermal activities, conductivity, catalytic activity, electrical conductivity, high selectivity, high surface area, functionalization, high specificity, and good biocompatibility. So these nanomaterials are used as artificial enzyme in many biological processes and act as substitute for the natural enzymes. We are known, there are different types of the natural enzymes like horseradish peroxidase, HRP, and alkaline phosphatase are attractive catalysts for the most of the biological reaction, which enhance the reactions 1,000 times. But they have many limitations. The artificial enzymes or the catalytically active nanomaterials shows numerous advantages over the natural enzymes, such as easy synthesis and high catalytic activity. Most importantly, high stability against the harsh conditions. So I have synthesized many types, several nanomaterials, in which these are some nanomaterials like graphene quantum dots, MOS2 quantum dots, and some nanocoordination polymers. Here we discussed about the electrochemical synthesis of the graphene quantum dots and their catalytic activity and further application in the sensing of the glucose. So this is the method for the preparation of the electrochemical graphene quantum dots. So the schematic representation of synthesis procedure of the electrochemical quantum dot shows that wood charcoal act as the working electrode, and graphene quantum dots prepared by electrooxidation of the wood charcoal. There are the two factors that are responsible for the formation of electrochemical graphene quantum dots. First one is electrochemical oxidation cleavage of the wood charcoal into multilayer graphene sheets, and second one is used electrolyte, ammonium persulfate ion, which produce further sulfate ion and which work as a strong oxidizing agent. Radicals in this process and sulfate ion radicals may function as sharp electrochemical scissors to cut down the graphene sheets into very small intact sp2 structures, namely quantum dots, by oxidizing the carbon-carbon bonds. So these are the characterizations of the quantum dots. Firstly, characterized by the TEM images. TEM images shows that figure A and B shows TEM images of the synthesized graphene quantum dots. The size range between the 3 and the 9 nanometer with the average size of 6 nanometer confirms the formation of the small size quantum dots. And figure B, which is the HRTM, shows the parallel lines of the graphite with a spacing almost 3.4 angstrom, indicates the crystallinity of the quantum dots. C images shows the AFM images, which shows the average height of the GQD almost 5 to 6 nanometer. Image D shows the UV visible spectroscopy, in which the lambda max 225 nanometer is due to the pi to pi star transition of the carbon-carbon double bond of the quantum dots, and lambda max 290 is due to the n to pi star transition of the carbonyl bond. And further, the Raman spectroscopy shows the D band at the 1363 centimeter inverse and G band at the 1582 centimeter inverse. FTI further used to identify the surface functional groups of the quantum dots, which are already presented here. So further, after synthesis, we have checked the catalytic activity of these nanomaterials and used a 3355 tetramethylbenzene TMB as a substrate. In starting, the in unoxidized form, TMB is colorless, but quantum dots here used as a catalyst which catalyze the TMB and give the product of the oxidized TMB, which is blue in the color. This is the basis for the detection of the our molecules, biomolecules, or glucose, etc. So here we can see that further we had applied a UV visible spectra in which the 652 nanometer peak shows the charge transfer complexes of the oxidized TMB and gets the blue color reaction in this. So these are the optimization parameters for the nanomaterials. HRP, which is in red lines, HRP, which is natural enzyme, shows less stability, but the nanomaterials, graphene quantum dots, shows high stability with respect to the temperature, pressure, and concentration of the H2O2. H2O2 is very essential in these reactions, which is produced by biomolecules, which I have discussed in the next slide. So on the basis of this principle, we can detect the range of or the amount of the different biomolecules like glucose, choline, cholesterol, etc. And in this, we can use a enzyme like for glucose, we can use glucose oxidase. So this and further confirmed by the UV visible spectroscopy. When we used a glucose oxidase and TMB, then the reaction takes place and charge transfer complex of the oxidized TMB formed and blue colored appear. So we can when we increase the amount of the glucose level, you can see in the image colorless glucose. Minimum amount of the glucose shows almost less color, but intensity is high. Intensity increased when the glucose level also increased. On the basis of this principle, we are preparing a kit for the detection of the glucose. Here the human serum and tear and saliva samples are used for the detection of these types of the biomolecule, especially for the glucose, and checked their reproducibility, repeatability, and selectivity, which are very high and specific. So this is the mechanism. For example, we are getting to determine the amount of the glucose. Then glucose and glucose oxidase combined and form gluconic acid plus H2O2. This H2O2 further used for the oxidation of the TMB, and here nanoparticles act as a catalyst. So in this method, glucose sensing by the colorimetric in serum sample compared with the autoanalyzer method. So there are the very less relative error. So almost this method is proposed and verified and almost very useful in further determination of biomolecules. So this is the further we had applied in the non-invasive samples like the tear and saliva also. So here we are getting cost-effective facile single-step large-scale synthesis of the nanomaterials, and which is very simple, inexpensive, sensitive, and high catalytic efficiency. Sensing results are very reproducible and specific, and the visual detection of the glucose in serum samples by the portable test kit be realized without any instrumentation or the complicated sensors design. And the proposed enzyme mimetic of the graphene quantum dot shows good potential for the application in various fields such as medical diagnosis, molecular biology, and any other diagnosis of the molecules. So these are my publications, and I have filed a patent for this work also. And we are going to prepared a portable test kit, which is very low, which are having very low cost. And these are the workshops and patent files also. Thank you DDU Gorakhpur University and IIT BHU for providing me facility for the research work. Thank you. Thank you, team.
Thank you, Dr. Vinita. Any questions? So I think there are no any question. So let us move for the next presentation is from Dr. T. Lakshmi Bai, SCSMB University, Tamil Nadu. Dr. T. Lakshmibai.
Yes, sir. Am I audible, sir?
Yeah. You can share your PPTs.
Is my PPT is visible, sir?
Yeah, it's visible.
Good afternoon, all. First, I thank you for giving me opportunity for presenting in ICFM-20. I am Dr. T. Lakshmibai from Sri Chandrasekharendra Saraswati Vishwamahavidyalaya University, Kanchipuram, Tamil Nadu. My topic is protection methods against threats in different layers of emerging cognitive radio networks. This is my lecture flow. Here the objectives, cognitive radio concepts and its functions, and the various attacks and detection systems, and conclusions, and so on. The introduction. Nowadays, smart materials plays a vital role in the design of sensors like biosensor and chemical sensor and pressure sensor. So many sensors which can be used for various fields like automation industry, chemical industry, home automation, and consumer products, mainly in medical field. For every application, the sensory information used to be collected from a remote place, and then it has to be sent wirelessly for processing. Such a wireless transmission requires frequency spectrum for data transmission. So I am focusing my talk on how the data from the sensors can be transmitted to the required destination with a limited available frequency spectrum. Nowadays, the frequency spectrum is very limited. And how to solve this problem? Here, nowadays, wireless networks based on fixed spectrums policy. That means the frequency spectrum is allocated for every user already. So the frequency spectrum which is available for the user, they are owned by licensed, and the utilization of it is only about 15 to 85% alone. So the inefficiency of spectrum usage and the limitations of the available spectrum which necessitate the new paradigm called cognitive radio. The cognitive radio is capable of reconfiguring itself using the environmental interactions to accommodate the transmission parameters. And also it enables dynamic spectrum allocation, thereby it provides efficient spectrum utilization. Dynamic spectrum allocation means the every user who are not at all own the licensed spectrum can also be using the available spectrum. So dynamically it can be allocated to every user who want to transmit their data. Here the primary user PUs are ensured better operation, and SUs are allowed to effectively use the available spectrum. These are some abbreviations I can use. CRN is the cognitive radio network, PU primary user, secondary user, MU the malicious user or harmful user, dynamic spectrum access is DSA, and PUEA is the main attack. This is the primary user emulation attack. QoS is the quality of service, and denial of service is DOS. The objective of is to detect the primary user emulation attack by using, if we are using the spectrum, there exists the attack. So that is the PUEA attack, and some other attacks also be available in the cognitive radio, and so we have to detect it for better utilization of the spectrum, and also to secure the network from the harmful, that is the malicious user who intend to waste the resources, and to propose a centralized system for the detection of primary attacks by using intelligent algorithm with adaptive key generation. To produce adaptive key, a intelligent learning center is used, which can detect the different parameters such as RSSI, energy, distance, and channel ID. Introduction. A number of wireless applications have been growing for over a last decade. So most of the frequency spectrum is already been licensed by some government agencies like FCC, and also it can be allocated to some another companies or as well as some of the organizations. Therefore, a apparent spectrum scarcity exists, and the frequency resources used are unbalanced. the efficiency of utilizing existing frequency resources has to be improved. Therefore, we need a dynamic spectrum access techniques were recently proposed to solve this spectrum inefficiency problem. So the cognitive radio exists. So it is the radio that can change its transmitter parameter based on interaction with the environment in which it operates. It has two characteristics. One is cognitive capability and other is the reconfigurability. Cognitive capability is nothing but to identify where the unused spectrum is available in a particular time, and that is called spectrum hole or white spaces. Reconfigurability. A cognitive radio can be programmed to transmit or receive a variety of frequencies and use different access technologies supported by its hardware design. Some of the concepts we can use is primary user who paid for a specific band, secondary user who have not paid but they want to use the frequency for communication, and the white spaces are spectrum hole which are exist in a specific time frame, a primary user who is not using his paid frequency channel. Handoff. When primary user comes to use his frequency, immediately the secondary user has to be quit and look for another white space. This is the spectrum hole. Here, in x-axis the time is taken, and in the y in this axis frequency is taken. So every user is using their frequency. So these are there are the primary users. So here in the first time frame, the primary user 1 is not using his frequency, and then he is using, and afterwards here he is not using. So this not usable, that is the unused spectrum, which can be given to some other fellow who wants definitely who wants to transfer the data. So these spaces are called spectrum hole or white space. The cognitive radio functions are the cognitive spectrum sensing. The spectrum sensing is nothing but finding the unused spectrum and sharing this with the other users. And spectrum management is nothing but capturing the best available spectrum for the secondary users. The mobility is whenever the secondary user, primary user comes into picture, then secondary user has to vacate. So therefore, while he is moving from one spectrum to another spectrum, there we should have ensure seamless communication. And spectrum sharing is nothing but providing fair spectrum scheduling method among coexisting other secondary users or CR users. This is the cognitive cycle. Here the radio environment is available. Here the cognitive radio which chooses the unused spectrum, and that is called spectrum sensing. After spectrum sensing, it has to decide in which spectrum it has to given to which secondary user. After it is decided, it is to be given to the secondary user, and they can use the spectrum, and the radio environment can be used. So that free space can be used. This is the cycle. Whenever this primary user, the paid user who come into the to use the spectrum, then immediately the cognitive radio which immediately tells the secondary user, and it has to mobile, so it has to move from that spectrum to another spectrum. So again the mobility comes into picture, and its decision is to be taken. So this is the cognitive radio cycle. And here the problem is, the key challenge in the cognitive radio network is to identify and aware about the presence of malicious user. Here the primary user and secondary user who are all using the spectrum. In the middle, some of the harmful users, malicious user, who can come into the picture and cause several degradation in the network performance. And here these are the attacks and some of the attacks and detection techniques. An attack is nothing but any activity that results in unacceptable interference to the licensed primary user. So the interference to the primary user, and for secondary user there exists the missed opportunities. So this is the attack. So the main attacks which are available in cognitive radio networks are primary user emulation attack, PUEA attack, and SSDFA attack, that is spectrum sensing data falsification attack. And the third attack is the cross layer attacks. First, the primary user emulation attack. Here the harmful user who can mimic as primary user. So this user can mimic the primary user. So what happens is, the secondary user believe the primary user is still in. So what happens? They can unable to use the white space. So these PUE attack are classified into selfish PUE attack and malicious PUE attack. Selfish PUE attack, the main objective of this attack is the malicious user wants to maximize his own usage. So the malicious PUE attack is they can abstract the dynamic spectrum access process. That means they exist the denial of service. To counteract this, what we can do is we have to propose filtering and we have to discard the duplicate signatures of the secondary users before communicating into base station. Therefore, here the advisory they can send fake signals and they can produce the random digital signatures, and because to make the secondary network to be inoperable. To prevent this, what we have to do is simple layer network encryption and also the authentication we should provide with a globally shared key. Next attack is the SSDF attack. So here what happens is because of the transmission features like fading, multipath fading. So because of this, at the receiver the signal power is reduced. So this makes the undetected primary signals and can harmful to the interference to the primary user. Here there are two types of fading occurs. One is shadow fading, which is frequency independent, and another is the multipath fading, which is frequency dependent. So this shadow fading is nothing but which causes hidden hole problem, in which the secondary user located within the transmission range of primary network who fails to detect the primary transmission. Here this is the diagram in which the primary user, here there are so many secondary users are there. This is the transmission passage of the primary user 1. Here the secondary user 1 is using the primary user's spectrum, but here the shadow fading occurs. Therefore the hidden node problem occurs. Therefore whenever the primary user wants to use his frequency spectrum, this secondary user cannot able to recognize. So in order to mitigate this one, what we can do is the central system, that is the fusion center, can be used. This system can be indicate whether the primary user is coming or not. That intimation can be sent to secondary user. Otherwise what we can do is this secondary user can observe, and also its own observation it can take decision, and also from the other secondary user it take the decision. So this can be done for avoiding the hidden node problem. And
Dr. Lakshmi, can you please accelerate your talk because you are running a little late?
Okay, sir. Okay, sir. Okay, sir. The next attack is the MAC layer attack. Here, MAC spoofing, conjunction attacks, and jamming attacks can be provided. And the last attack is the cross layer attack. So far, what we have seen is the PUA attack. Those are for a particular layer alone. But the cross layer attack, the adversaries which attacks targeting the multiple layers. So this is the cross layer attack. And here the table which can give the what the types of attack and in which layer it will affect, and the main characteristics are given here. And the conclusions: the demand for internet traffic through wireless infrastructures has increased substantially due to the widespread use of smartphone and then online services and the reduced subscription cost. So the immediate effect what it increases crowding, overcrowding of ISM band. Therefore this discussion presents the most important contributions on security threats and detection techniques. The future scope is the inclusion of optimization algorithm can impart more accurate classification and detection of the attacks, and then we can implement new intelligent algorithm which is to be integrated for recognizing more attacks, and design of test bench needs more versatility in order to support more variety of transceivers. Thank you. Thank you very much for giving me the opportunity, sir.
Thank you, Dr. T. Lakshmi, for giving a nice lecture on wireless spectrum. Any questions? If there are no questions, we'll move for the next presentation by Dr. Abhishek Kumar Gupta. is from MMUT, Gorakhpur. Abhishek Kumar Gupta. I think Abhishek Kumar Gupta has not joined yet. So I will invite next speaker, next presentation by Dr. Ankit Kumar Vishwakarma. Dr. Ankit Kumar Vishwakarma.
Okay, sir.
Okay. Start your presentations.
Please respect the time, that is 10 minutes for the oral presentation. So if you will finish on the time, it will be convenient for the next speaker as well. So thank you.
Good afternoon, all of you, sir. I am Ankit Kumar Vishwakarma from DDU Gorakhpur University, Gorakhpur. My presenting paper title is Microstructural and Optical Property of CDS Dope ZNO Nano Thick Film. It can outline, abstract, introduction, experimental detail, fabrication of thick film, characterization, result and discussion, XRD, atomic force microscope, UV visual spectroscopy, conclusion and responses. Abstract. We fabricate undoped zinc oxide and cadmium sulfide doped zinc oxide thick film and investigated the structural, morphological and optical property. Two simple undoped ZNO and 2 beta% CDS doped ZNO thick film have been fabricated on glass substrate. The fabricated film are characterized by XRD, atomic force microscope and UV spectroscopy. The fabricated sample are so that the crystallite size, grain size, band gap are decreases with CDS doping. Introduction. In the recent year, nanotechnology has been established its application in various fields of science and technology. Presently, nanometer with small, less than 100 nanometer, widely studied by various researchers due to their unique properties such as physical, chemical, optical, which drastically change due to the large surface to volume ratio, reduces particle size. ZNO is a widely band gap intrinsic N-type semiconductor is one of the most widely studied material for UV light emitting diode, solar cell, field emission, gas sensor, etc. There are several methods used to fabricate ZNO thin film, such as spray pulses route, Soldier method, RF magnetron sputtering method, pulse laser deposition method, etc. ADHR et al. Reported the effect of CD doping on the electrical optical property of ZNO thin film using spray pulses route, and he showed that the crystallite size, grain size, and band gap decreases with increasing of CD concentration. Dinesh et al. Investigated the CD ZNO powder nanocomposite synthesized wide sample mechanically allowing method, and he suggested a CD ZNO is giving photoluminescence spectra, indicating the large rate shift in the visual region, and it is useful for solar cell application. K. Purnima et al. Also described the CU doped ZNO nanostructure thin film for solar cell application. B. Fabry et al. Have studied the electrical, optical, and sensing property of photoactivated ZNO thin film. A.K. Yadava et al. A.K. Yadava et al. Presented the X-ray absorption spectroscopy of MN doped ZNO thin film prepared by RF sputtering technique. Dhruvasi et al. Presented the effect of cobalt and ZNO thin film deposited by Soldier method, and he found that the band gap was increasing with range of 3.26 to 3.31 electron volt with CO doping increases, it decreasing for higher doping CO content. The efficiency of the ZNO based device like as solar cell hampering due to wide band gap of ZNO. For enhancing the efficiency, it is imperative to couple up the wide band gap semiconductor with the lattice match visual sensitizer. CDS lattice structure is same as ZNO. Thus, CDS is most suitable visual sensitizer for the ZNO. Fabrication of ZNO nano thick film. Two sample undoped ZNO and 2 beta% CDS doped ZNO are fabricated on glass substrate. Initially, we can take some amount of ZNO in a porcelain grind it some time. After 1 to 2 hours, and some amount of labeling are added, and there are some solvent such as acetic acid are added on it. And there are to make the ZNO and CDS paste, and the thick film are prepared using printed on the alumina substrate and also glass substrate. Here it is the preparation of, also here we can show the preparation of undoped and ZNO, undoped and CDS doped ZNO thin film. Result and discussion. XRD. The crystal structure of fabricated sample was analyzed using XRD measurement. The crystallite was estimated using device error formula, and we found that here the XRD pattern are shown here. We can say the CDS is affected on the ZNO, and the intensity are also decreases with CDS doping. Here some extra peaks such as hatch is appeared. It is effect of CDS. XRD analysis performed the investigated the crystallized lattice parameter and microstain of the fabricated ZNO and ZNO CDS composite. XRD pattern was fabricated film are shown in this figure, and it is found that the crystallite size is 45 nanometer to 38 nanometer, and we found that the crystallite size is reduced with CDS doping. We also calculate the lattice parameter of ZNO, and it is well matched the hexagonal structure of the ZNO, and it is a 3.31 nanometer and 5.636 nanometer respectively. Atomic force microscope. The surface morphological property of ZNO and ZNO CDS are presented by atomic force microscopy, and the result here shown 3D, three-dimensional, and histogram of the ZNO and CDS doped ZNO thick film here presented here. It is a 2% CDS doping ZNO, and it is a three-dimensional, and it is a histogram of CDS and CDS doped ZNO. Here, crystallite size, microstain, grain size, roughness, and band gap energy of undoped and CDS doped ZNO are presented here. For undoped ZNO thick film, crystallite size is 45 nanometer. Microstain is a 0.6453 nanometer. Grain size 167.31, and roughness parameter 23.89, and band gap is a 3.18. But with CDS doping, the crystalline size is reduced, and it is a 1338, and band gap is a 2.1 electron volt. Optical property. The optical property of fabricated sample were investigated using UV visual spectrometer. Operating range 300 to 850 nanometer. The optical band gap of fabricated sample was estimated using torque relation. The band gap was determined by extrapolation of the linear region of alpha h nu versus alpha h nu, and it is shown in this figure. It is shown in this here in this figure. UV visual absorption spectra of ZNO and 2% CDS doped ZNO, and here the linear interpolation of the undoped and CDS doped ZNO. We can found that the band gap of CDS 3.18 electron, and with CDS doping 2.1 electron volt. Conclusion. In the present investigation, microstructural optical property of ZNO and ZNO CDS doped thin film are reported. XRD, FAM analysis, and UV visual are indicated for crystallite and grain size and band gap energy. The crystallite size was decreases from 45 nanometer to 38 nanometer with CDS content. The grain size and roughness reduces from 67.31 to 36.81 nanometer, and roughness to 23.89 to 13.89 nanometer respectively. It is evident from the UV visual spectra that the optical band gap energy decreases from 3.18 electron volt to 2.1 electron volt with 2% CDS doping in ZNO. And it is observed that absorption band gap of ZNO is redshift in visual region. The lattice parameter of ZNO and CDS doped ZNO is evaluated, and it is the same which confirmed that the fabricated CDS doped ZNO thick film are polycrystalline nature of arzite. References, and thank you, sir.
Thank you, Ankit. You have presented very nice presentation on nano thick film.
Thank you, sir.
But you have reported crystallite size and grain size.
Okay, sir.
Both are approximately same. Can you differentiate?
No, sir. Crystallite size was 45 nanometer to 38 nanometer, and grain size 36.
Crystallite size of 38 nanometer and grain size.
Grain size 77.31 nanometer to 36.81 nanometer.
In one case, you have reported 38 nanometer crystallite size and grain
36.81 nanometers grain size for CDS doped ZNO nano thick film.
I request Professor DP Singh to conduct the session.
Okay, thank you, Amrish. Thank you, Dr. Yadav. So thank you, Dr. Verma, for a nice talk. So now next talk is with Ms. Pallavi Sharma from DDUGU, Gorakhpur. So I request Pallavi Sharma to start her talk. You have 10 minutes for the presentation. Please respect the time, as it will be convenient for the next speaker. Ms. Pallavi Sharma, are you available? Ms. Pallavi Sharma, can you activate your microphone, please, because your voice is not audible.
Am I audible, sir?
Yeah, thank you. Thank you.
Thank
Please
you,
go
sir.
ahead.
Thank you, sir. Good afternoon, everyone. I am Pallavi Sharma. I'm a research scholar in DDU Gorakhpur University. And today my topic of presentation is fungal mycelium foams as an alternative to detrimental plastic materials. So, introduction is that in today's time, environmental pollution is a very big problem, and especially non-biodegradable wastes are polluting our environment, polluting soil, air, and water bodies. So today we produce 300 million tons of waste every day. That's nearly equivalent to the weight of entire human population. Only 9% of all plastic waste ever produced have been recycled, and about 12% have been incinerated, while rest 79% has accumulated in landfills, dumps, and natural environment. We strongly need to stop using plastic or minimizing the use of plastic to save our environment. And fungal mycelium can be good source for organic plastic. So that is a normal plastic material that we use in our daily lives, and polystyrene that we use is it is also non-biodegradable waste, and it also pollute our environment, generate a lot of waste. So I'm going to talk about mycelium, how mycelium can form fungus, how fungus can form organic plastic. So the fungus have their own kind of kingdom of life, separate from plants and animals. Majority of fungus has complex interconnecting web of microscopic threads called hyphae. Here in this picture, we can see fungal hyphae. These are microscopic threads. These hyphae can extend up to great distance in soil. The largest organism in world is a fungus stretching 9.6 square kilometers. Mycelium is the mass of branch hyphae of fungi. Mycelium is mainly composed of natural polymers as chitin, cellulose, proteins. So it is a natural polymeric composite fibrous material. Fungus, when grown on organic waste, then it decomposes it and simultaneously glues the particles and forms solid object which can be given desirable shape. It has been a lot of plastic-like material has been formed by using fungal mycelium. This is a species of fungus which is called oyster mushroom. It is being used. It can be used in developing organic plastic. This is mycelium, you can see, and this is the fruiting body of that fungus. So the mycelium-based plastic can be produced by two ways. By one way, by decomposing organic waste or by using pure mycelium. So this is a brick made from fungal hyphae, fungal brick prototypes made from rice hulls and glass fine waste. This is also 3D printed mycelium made from fungi, and these pictures, these objects are made by fungal mycelium. And this polystyrene-like object, which is being packed, it is also made from fungal mycelium. So, fungal mycelium is cost-effective, lightweight, insulating, hydrophobic, flame-resistant material, and it is used using less energy. Tons of polystyrene blocks, landfills pollute the oceans and pollute our environment. But this fungal foam is 100% natural, 100% biodegradable, and it breaks just in few weeks. It has a short lifespan, but it can be used as organic fertilizer after after it is destroyed. So what the same fungus can be grown in different conditions to get different type of end product, like cork like light material, rubber like material, plastic like material. This field needs attention of scientific researchers. Fungal mycelium can be best alternatives of plastics in future. So I'm not going to take a lot of time, and this is reference, and thank you. Thank you, sir.
Thank you, Ms. Sharma, for your timely presentation. Your talk was really very interesting, especially the generation of fungus and how to remove it. Especially, I could see this problem in the wine sipper in France, because France is one of the most like highly producing country which produce the wine on the large scale. So definitely it could be a bit better option that your research will be integrated on such topic. Now, I think Dr. Ambrish has some announcement. So I hand over this session to him for the announcement, and after that we will continue this session. Thank you.
Thank you, Dr. Singh. I just want to tell you all that we also conducting a poster presentation session in this conference. So this will be, I think, first virtual poster presentation, if not in India, then in Uttar Pradesh. I'm very sure. So to go to this poster presentation, I just want to show you the conference website. Is my screen visible?
Yes, Ambrish is visible.
Yes. So this is the conference website. You need to go to poster presentation, and you will see the name of presenter here in the order, in alphabetical order actually. So in order to see the poster of any presenter, you need to click the name and it will lead to an external website, and you will see the poster. Now, in order to ask any question or query, you just need to enter your comment. That's all, I think. So I just invite you all to participate in this virtual poster session as well, to make it a success. Thank you.
Thank you, Dr. Amrish. So now I
1 minute, sir. 1 minute, sir. Okay. So I will put the links to conference website as well as a direct link to poster website in the chat box. Dr. Singh, please continue.
Thank you, Amrish. Now I invite Dr. Ekta Sonkar from Gorakhpur University for her presentation. Dr. Ekta, are you available?
Yes, sir. Hello.
Yeah, please
Yes,
continue your presentation. Please share your screen.
Okay, sir, I'm sharing.
Okay, you have 10 minutes for the presentation.
Okay, sir. Thank you, sir. Thank you so much. Good evening, everyone. This is Ekta Sonkar. I am working as an assistant professor in Department of Chemistry, DD Gorakhpur University. Today, I am going to give a short presentation on my topic, perylene and diphentyl solar cell. Before going to talk about the main work, first of all, I would like to tell what is polymers. Polymers are the copolymers that are formed by the conjugation reaction of the dianhydride monomer with diamine monomers. Now, this conjugated polymide means the polymide backbone must contain alternating single and double bonds so that upon doping with some dopants, charge carriers can be generated in the polymeric backbone, and the movement of this charge carrier along the polymeric backbone will contribute to the electrical conductivity of this conjugated polymer. Now, here I am using organic monomer for the synthesis of this conjugated photochemically stable, and they show strong absorption and emission properties. So the aim of my work is to synthesize a biconjugated conducting polymer with better solubility, better absorption property, and small band gap. For this purpose, I am first time reported the synthesis of safranine and perylene-based conjugated donor-accepted polymide using conjugation polymerization technique. This design using conjugated polymide containing alternate electron accepting and electron donating segment in the polymer backbone generates an internal charge transfer that lowers the band gap of the polymer, and as a result, this conjugated polymide absorb at longer wavelength. This is the synthetic route for the polymer synthesis of the polymer. Here, the perylene tetracarboxylic dianhydride reacts with the session O group under nitrogen atmosphere at 150 degrees centigrade using imidazole and dimethylacetamide as a solvent to give this conjugated polymide. Here, this perylene di acts as an electron accepting unit, whereas the safranine moiety acts as an electron donating unit. Now, this synthesized polymide has been characterized by various spectral, optical, electro-optical, and thermal techniques. This is the 1H NMR spectrum of the synthesized polymide. In 1H NMR spectrum, a broad peak was observed in the range of 7 to 9 ppm, which is corresponding to this aromatic proton signal of the perylene dye and safranine O moiety. Here, the peak appeared at around 2 ppm, was corresponding to this methylene proton of the safranine O group. Here, the disappearance of this terminal amino group of the safranine O moiety indicates the formation of the polymer with complete conversion of the monomers. This is the IR spectrum of the synthesized polymide and its monomers. In the IR spectrum of the perylene dye, carbonyl stretching vibration of the anhydride group was appeared at 1700 centimeter inverse, and in the IR spectrum of the Session-VII group, the NH stretching vibration was appeared at around 3300 centimeter inverse. But in the IR spectrum of the polymer, the NH stretching vibration is completely disappeared, and the carbonyl stretching vibration of the anhydride group is also disappeared, and a new peak was appeared at around 1600 centimeter, which is corresponding to the carbonyl stretching vibration of the amide group. So here the disappearance of the disappearance of the amine energy stretching vibration and carbonyl vibration of an anhydride group indicates the formation of the polyamide with complete conversion of the monomers. Now the thermal stability of the polyamide was determined with the help of thermogravimetric analysis. This is the TG curve of the conjugated polyamide. Here the first weight loss at around 100 degrees centigrade corresponding to the loss of the solvent molecule trapped inside the polymeric backbone, and the final weight loss started at around 480 degrees centigrade, which is corresponding to the decomposition and degradation of the polymeric backbone. So this polymer is thermally more stable than their monomers. This is the GPC chromatogram of the polymer. The average molecular weight of the polyamide was determined with the help of the gel permeation chromatography. Here in gel permeation chromatography, the average molecular weight of the polyamide was calculated at 50,380. So this is the polyamide synthesized by this technique confirm the formation of this polymer. The morphological behavior of the synthesized conjugated polyamide can be studied with the help of XRD pattern. Here in XRD, in this figure represents the XRD curve of the polymer. In XRD curve, a broad peak was appeared between 18 to 38 degrees, which indicates that the synthesized polyamide is amorphous in nature. Here, some small peak was also appeared that gives the semi-crystalline nature also. Now, the UV visual and cyclic voltammetric study. The UV visual study is helpful to know the extent of pi conjugation in the conjugated polymer. Here we have seen three types of peaks. This peak is corresponding to the pi to pi and to pi transition of the perylene dye, and here a baseline are drawn. Because the onset value is not completely offered. So from this baseline value, they can calculate the band gap between HOMO and LUMO energy level using this relation. That is, band gap is equal to 1 to 4.2 upon lambda. This lambda is this onset value, and by using this relation, the band gap of the polymer is calculated as 2.23 electron volt. Now, cyclic voltammetric study. The electrochemical behavior of this conjugated polyamide can be studied with the help of cyclic voltammetry. Here, the figure represents the oxidation and reduction peak potential related to the current potential voltammograms. Here, the formal redox potential value can be calculated using this relation. Here, EPA and EPC are the anodic peak potential and EPC is the cathodic peak potential. And the value of formal redox potential is observed at 0.38 volt. This value of formal redox potential can be used for the construction of the energy level of diagram of the sensitizer, as it gives the electron donating energy level in its ground state. Now, electrical conductivity study. To study the electrical conductivity of the synthesized polyamide, the electrical conductivity of the synthesized polyamide can be studied with the help of impedance analyzer. If the Nyquist plot of the polyamide at different temperature. Here, the value of Rb can be determined from the semicircular R on the real FF of the Nyquist plot, and the dc conductivity can be calculated using this relation where 1 by Rb that is 1 by Rb into L by A. Rb is the bulk resistance, L is the thickness of the polymeric film, A is the area of sample holder. The dc conductivity of the polyamide, if calculated as 10 to the power minus 5 Feynman per centimeter at room temperature, which increased up to 10 to the power minus 4 Feynman per centimeter at higher temperature due to increase in chain flexibility at higher temperature. The figure B represents the temperature dependent dc conductivity. In the temperature dependent dc conductivity shows Arrhenius type behavior, and here the conductivity increases with increasing the temperature and follows Arrhenius like behavior with thermally activated process. Energy level diagram. The figure represents the relative position of the electron exchange energy level of various cell components, that is TiO2, polymer phosphatizer, and Perovskite. And this figure represents the current potential curve of DFFE assembly in dark and illuminated condition. Here, the solar to electrical energy conversion efficiency can be calculated using this equation, and fill factor was calculated using this equation, where JFP represents the short circuit photocurrent, VOC is the stand for open circuit photovoltaic, FF is the fill factor, I is the intensity of the incoming light, Jmax and Vmax are maximum current and maximum potential respectively, and its value are shown here. Now conclusion. Here, a new thermally stable and conjugated polyamide containing electron accepting perylene and electron donating Triphenylene-pentaalkynylbenzene was successfully synthesized for the first time by condensation polymerization technique. The 1H NMR, IR and JPC analysis confirmed the formation of the polymer. The synthesized polymer has high thermal stability, low band gap, and show good absorption properties. The electrical conductivity study of polymers shows the dc conductivity of the polymer 10 to the 4 7 per centimeter at 100 degrees centigrade, and the temperature dependent dc conductivity follows Arrhenius type behavior. The developed donor accepted polymer can successfully be used as phosphatizer for TiO2-based diphenthite solar cell. These are my list of publications. Thank you for your kind attention. Thank you.
Thank you, Dr. Ekta, for such a nice presentation. I think we are running a little short of time, so there is no question time for here. But if you have question to Dr. Ekta, you can put the question in the chat box. Now I invite the last speaker of this session, Dr. Pyare Lal from BV University, Banasthi University, Rajasthan. So I request Dr. Pyare Lal to start.
Am I audible, sir?
Yeah, you are audible. Please share your screen and go ahead, please.
Thank you, sir. The title of my presentation: Graded Diffraction Index Nanolayers Influenced Several Light Properties of Aluminum Gallium Arsenide Type Futuristic Material. Now, aim of my presentation and introduction. This presentation provides a crucial contribution in the optimization of the several types of properties of intensity of light of aluminum gallium arsenide type futuristic material under the influence of number of several graded diffraction index nanolayers. The spectral type behaviors of model confinement gain per centimeter with wavelengths of photons and performance of peak model confinement gain with the number of several graded diffraction index nanolayers for proposed futuristic material have been illustrated by graphical results. The changeable performance of indications of diffraction with current densities and typical behaviors of a range of model and guiding parameters with carriers per cube centimeter have also been calculated by appropriate simulated techniques. Under graphically performance, the maximum value of achieved model confinement light gain has been obtained by simulation approaches at the wavelength of 830 nanometer. This 830 nanometer range of wavelength has been utilized in the telecommunication systems using TIR method through optical fiber cables. This type
Excuse me,
wavelengths
Dr. Pyare.
has, yes sir,
Your slide is not moving. Is there any issue from your side?
yes sir. Also been useful in the combination of higher radiation power and cellular interactions. First of all, we define light. We know that light is the part of electromagnetic wave whose wavelength range 380 nanometer to 780 nanometer becomes it travels in vacuum with velocity of 3 into 10 power meter per second. The definition of light is existed in the spelling of light. L stands for linear propagation. Light always propagates in the rectangular straight line. I stands for invisible. Light becomes invisible, but the objects are visible by the light. G stands for group of 7 colors. We've got H stands for heat of energy, heat or energy. So light is a form of energy, and T stands for transverse electromagnetic wave. Now discuss about science. Science comes from scientific word, which name means study specific knowledge of 7 types of specific. S for systematic, C stands for continuous, I stands for innovative, E stands for experimental, N stands for natural, C stands for correlated with engineering and technology, E stands for explorable. Now we discuss about heterojunction. Heterogeneous structure. The combination of multiple heterojunction is called heterogeneous structure, and heterojunction is the interface between the two different band gap materials. Aluminum gallium arsenide is the nano heterogeneous structure. Heterostructures are several types. Stain HCH means stain type, step type, index nano scale confinement heterostructure. And green SCH means graded refractive index nano scale confinement heterostructure. This is the optical gain equation as a function of energy of photon. In general, light gain is the enhancement in the intensity of light per unit initial light and per unit length of, so its Hz unit is per centimeter. It's affected by temperature, width of active layer, strain, as well as nature of material. This is the equation of refractive exchange. Now resultant discussion. The figure represents the changeable spectral behavior of model light gain with photonic wavelength by left y-axis and bottom x-axis respectively, and variations in peak model type gain with number of graded refractive index nanolayers by right y-axis and top x-axis respectively. The value of photonic wavelength and at which model gain or model light profit is 0 called transparency wavelength, and this condition is called transparency condition. In these conditions, the stimulated emission is equal to absorption. Above the transparency wavelength, the threshold wavelength, the model gain is achieved due to increase in stimulated emission rate. The maximum gain is obtained at the 830 nanometer. This is called lasing wavelength. Moreover, when the number of graded refractive index layers are decreased, then model confinement factor is reduced. So model gain is enhanced because it is directly behavior with the model confinement factor. And in first figure, this figure, right y-axis and top x-axis are represents the variations in peak model gain versus number of graded refractive index nanolayers. The peak model gain is enhanced as increase in number of graded refractive index layers due to increase in value of model confinement factor. When we go from active region to cladding layers, then confinement factor tends to decrease. This figure represents the changeable behavior of refractive index change, which current densities are given by left y-axis and bottom x-axis. Change in refractive index has inversely behavior with current density, and right y-axis and top x-axis represents the anti-guiding factor versus carrier concentrations. It has proportional behavior with the carrier concentrations. Moreover, when the number of graded refractive layers increase, the change in refractive index is decreased and anti-guiding factor shifted towards its higher value. And last, This figure shows the performance of size of green layers versus number of green layers and changing behavior of saturated model gain versus saturated wavelength for aluminum gallium arsenide have been shown in this figure. It is clear by results of that both the performance of size of green layers and changing behavior of saturated model gain provide the reciprocal behavior with number of green layers and wavelength respectively. This figure represents the performance of peak gain compression and range of anti-guiding factor with number of green layers and maximum change in index of reflection respectively. And last, this figure shows the behavior of optical loss and peak optical gain with lasing wavelength and percentage compressive strain. It is clear by black graph that the loss in minimum at wavelength is of 830 nanometer. So this type photovoltaic material is very useful in the fiber optics communications. Now conclusion. The maximum model gain is achieved at the lasing wavelength 830 nanometer. This wavelength range has been utilized by the process of total internal reflection in optical fiber for the purpose of telecommunications system with minimal attenuation. 830 nanometer wavelength has also been utilized in the determining the combination of higher penetration power and cellular interactions. And last, the wavelength 830 nanometer has very important role in the medical science for the treatment of skin disease. Thank you, sir. Thank you, sir.
Thank you, Dr. Parelal, for this nice lecture on the 2D structure materials.
Thank you, sir. Thank you.
So basically, it is my privilege to welcome Professor Neeraj Mishra from the Department of Physics, University of Lucknow.
Yes, sir. Yes.
He has been our teacher also as well at the University of Lucknow, and he taught us quantum mechanics to me and to Dr. Amrish as well. So
Yes,
on behalf of the conference organizing committee and chairperson, I welcome you, Professor Neeraj Mishra, sir. And this was the last presentation from this session, in which we had one talk and one invited talk from Republic of Korea. And in addition, we have 6 oral presentations on different topics. And it is really very nice to see the lectures from all over the field of science and technology. So on behalf of organizing committee, please let us join to thank all the speakers of this session. And here we announce the ending of session, which is the last session of this. And with this word, I transfer to host Dr. A.K. Srivastav, who will give some announcement regarding the validatory function of this conference. Thank you all. Thank you all the speakers to joining us in this conference. Thank you for your time and your lectures.
Thank you. So I would like to thank the esteemed presence of my PhD thesis advisor, Professor Neeraj Mishra, sir, from University of Lucknow. And I would also like to thank Professor Umesh Yadav, sir, and Dr. D.P. Singh for chairing this particular session. Now, I would like to invite all of you to the valedictory session of this international conference on futuristic materials. I look forward to welcome you all in the last and very important session of any conference, I think. So I would look forward to welcome you. The link will be same, and we will start the valedictory session from 5 p.m. onwards. So with this small announcement, I would like to end this meeting. Thank you. Thank you all.
Dr. Amrish, how much time we have for the valedictory function? Just in minutes, like?
About half an hour.
Half an hour. Okay, because time zone is different for me. So
yes, Dr. Singh, I can understand. You are in French time zone. Thank you.
Yeah. Thank you so much.